So let's see our lesson 3.7 on rational function. Again, that is of the form f of x is equal to ax, that's your numerator, over bx, that is your denominator. So in here, you would always have to have a variable, right, but typically x on the denominator, okay? Good. So that is our rational function. But before we consider some of the key features, let's see first the summary in here and our learning objectives for this particular rational function case. Okay, so here it is. Okay, let's read in here what our objectives are, learning objectives are for this lesson, all right? Sunny, go ahead.
Use arrow notation, solve applied problems involving rational functions, find the domains of rational functions, identify vertical asymptotes, identify horizontal asymptotes, and graph rational functions.
Thank you, all right? So we're going to deal with first analyzing the key features of our rational functions, right? Typically the what? The domain and range as well, the vertical and horizontal asymptotes, and how to graph rational functions. Okay, well, first of all, what do we mean by an asymptote, right? So check on your definitions, and obviously if you are familiar with the definition of an asymptote, you can check it out in there as well. Okay, so here it is. All right, let's read some definitions in here of vertical and horizontal asymptote. Okay, Adam, let's read what a vertical asymptote is. Go ahead, please. Okay, on your summary, go ahead.
The vertical asymptote of a graph is a vertical line x equals a, where the graph tends towards positive or negative infinity as the input approaches a from either the left or the right.
Thank you. All right, and we got the notation in here for such. All right, once again, that's our vertical asymptote. Now, later we're gonna see that the vertical asymptote is dependent on the numerator or the denominator. Which one? Logan, where do you think is the vertical asymptote depending on? The numerator or the denominator?
The denominator?
The denominator, right? So you set the denominator as 0, solve for those x values, thank you, and you're gonna get the vertical asymptote, right? So we're gonna see that one later, but as you may notice in here, for example, for this graph, the two vertical asymptotes, let's call them VAs, are such, right? See this VA in here and VA in there, right? Those are the two vertical asymptotes. Are we good? Got it? Okay. Sometimes there's one vertical asymptote, sometimes there's no vertical asymptote, right? Sometimes there's more than one. In this case, 2. You good? All right. Let's now read what we mean by, so again, the bx in here is the what? The denominator, right? So again, the vertical asymptote, let's call it once again VA, depends on the denominator. Okay. Let's now read the horizontal asymptote. Okay, Bryce, go ahead. Let's read what horizontal asymptote in here tells us.
A horizontal asymptote of the graph is a horizontal line y equals b where the graph approaches the line as inputs increase or decrease without bounds.
Thank you. All right. So there we go. Horizontal asymptote. Okay. As you may notice in here, the horizontal asymptote actually explains or gives us an idea on what the range will be. Okay. And as you may notice in here, the horizontal asymptote depends on what? The degree, right? The highest exponent or the degree of the numerator and denominator. Good. Let's read those 3 cases for such, right? Emma, let's read the first case. If
degree ax is what's the degree bx?
HA.
HA at y equals 0.
Correct. Automatic. Y is that equal, the line y equals 0 is the HA or horizontal asymptote. Should the numerator degree be less than the denominator degree? Are we good? Right? That's case number 1, right? If numerator degree is less than denominator degree, automatic y equals 0. Okay, no need to solve for anything, okay? Let's read case number 2. Victor, go ahead, please.
Case number 2.
If degree AX
If degree AX equals degree BX,
y equals
Y equals
what's that? Lead coefficient
lead coefficient of B
of A over.
over lead coefficient of B.
Thank you, right? So again, if both up and down, the numerator and denominator has the same degree, for example, they're both degree 3, what do? Just look at the lead coefficient above, look at the lead coefficient below, divide those two together, that would be the horizontal asymptote. You get it? Okay. Last one, case number 3, right? Let's read case number 3 in here. Kelly, let's go ahead. Let's read case number 3. If
degree AX is greater than degree BX, use synthetic division to get
slant asymptote, right? It's not gonna have a horizontal asymptote. It's gonna have a slant asymptote, right? Again, should the numerator have a bigger degree than the denominator, you can either use synthetic or long division, right? Get the quotient, that will be your slant asymptote, okay? It's not gonna be a horizontal asymptote, but it's gonna be slant. Get it? Okay. So as you may notice in here, there's a horizontal asymptote for such, and that is where, you see this one in red, right? That's the horizontal asymptote, okay? And actually, the horizontal asymptote defines the what? The right end behavior and the left end behavior, right? So look at the horizontal asymptote. This is the right end behavior, right? Right end. As x goes to infinity, right? Your y goes to where? Horizontal asymptote. We good? Right? Similarly, on the left end behavior, left end, as your x goes to negative infinity, like leftmost, your y tends to what? Get near the what? The HA, or horizontal asymptote. Get it? So again, as you may notice in here, the horizontal asymptote typically gives you an idea on the left end and the right end behavior. Get it? Okay. So as you may notice in here, those are the left end and right end behavior. Okay. What else have we not discussed yet? Right. So once again, the domain depends on the vertical asymptote. The range depends on the horizontal asymptote. Right. What other key features are in there as well? We also have what we call whole, or what we call removable discontinuity. Right. You would notice in here, like such. You see that one, guys, right? In Desmos, you cannot see that one as a whole, like what you call this? Hollow circle, right? But if you go click your browser in there, right? It's gonna be undefined. Get it? Okay. So this one, if you hover your value in there, it's gonna be what? Like say in here, whole, that value of x, and then you would see what? The word undefined. Get it? Yeah. And again, that's what we call our removable discontinuity, right? Where does it happen? Well, let's read. Giselle, where does it happen? The whole or possible removable discontinuity? Go ahead. At
common factors of A and B.
Thank you, right? If the numerator and denominator has the same common factor, let's say there's an x plus 1 up, there's also an x plus 1 down, typically you're gonna cancel them, right? That's already the whole, right? At negative 1 in that case, at that x value. Get it? Okay. Again, you're not gonna see it on the graph, but if you click your browser in there, you're gonna see a point of what? That x value of the whole, comma, undefined. Get it? Okay. What else do we have in here? The intercepts. Let's read how do we get the intercepts for such. Thomas, go ahead.
X-intercepts were numerator, and that's equal to 0.
Thank you, right? Whatever your a of x is, set it equal to 0. So for those x's, those will be your x-intercepts. Get it? Again, right after you got the whole, after you cancel the common factor up and down, then you can get the x-intercepts, okay? Last one. If there's an x-intercept, What's the other one? Aiden, go ahead.
Y-intercepts at x equals 0 or consider the constant terms.
Thank you, right? So there are two options for such, right? If it's in factored form, set your x's to 0, right? If it's in standard form, both up and down, just look at the what? The constant terms above and below. That ratio is your y-intercept. Get it? Okay. Well, let us answer some questions in here for such, analyzing these in here, guys, okay? Let's read in here, number 6, 7, and 8. What do we do with this? Okay, Marguerite, let's read that one.
For the following exercises, find the domain of the rational function.
Thank you, all right. So in here, it says find the domain of the rational function. Well, choose a number for us, Marguerite. 6, 7, or 8? 8. Let's see number 8, okay? So, let me just put it in here for number 8. Again, we're looking for the domain, right? Domain. So it says in here the following, what's that? F of x is equal to what? X squared plus 4 all over, what's this? X squared minus 2x minus 8. Get it, guys? Okay. Again, how do we find the domain? What do we do? Read it in here. Jaden.
B of x equals 0.
Yeah. So set the b of x to 0, right? To get the domain, right? So domain x where b of x not equal to 0. So where's your b of x? The denominator, right? You see the denominator? Set it equal to 0. Right? X squared minus 2x minus 8 cannot be equal to 0, right? That's your domain. You can do quadratic factoring, you can do graphing, you can do quadratic formula, any quadratic factoring techniques, right? Okay, what do you get from here? What two numbers will multiply to -8 and add up to -2? Hint, they are different signs, right? Yes.
-4 and 2.
Thank you, right? Very good. X minus 4, x plus 2. Got it? Okay. And then, again, you can verify your answer by either, again, graphing it. Let's see what we got. So from here, x minus 4 is not equal to 0. That means x is not equal to 4. Get it? Okay. Other one, what? X plus 2 is not equal to 0. That means your x is not equal to what? Eva, what do you think?
-2.
Negative, right? So, here we go. Okay. So what's your domain? Your x is what? Everything except 4 and -2. Are we good? All real numbers except 4 and -2, right? 13. How are you gonna write it in interval notation? So here it is, right? So for the domain, what's that gonna be? X is equal to, well, -infinity to infinity, right? Except what? -4, -2 and 4, right? So -infinity to -2, and then what else? -2 to 4, and then 4 to infinity, right? Get it, guys? Right? So that means it's from negative infinity to infinity, means all real numbers except what? -2 and +4. Are we good? Get it, guys? Again, you can verify it by graphing, okay? Let's see. How do you verify it by graphing? Well, let's just graph it in here, number 8, and see how it looks like, right? Y or f of x is equal to, what did it say? X squared plus 4, right? Over x squared minus 2x minus 8. Okay, get it, guys? Okay. Where are your VAs, your vertical asymptotes? Well, it says at x equals 4, see that one in red? Okay. And at x equals equals -2. You see that one in blue? Get it, guys? Get it? Okay. So what are your domain? Your domain basically is what? All real numbers except those vertical asymptotes. In short, from -infinity to -2, right? -2 to 4 for this piece, and in here, 4 to infinity for that piece. Questions? Questions? Again, those are your VAs or vertical asymptotes, okay? Questions regarding that one, guys? Okay. Well, let's continue, right? It's not being asked in there, but where do you think is the horizontal asymptote for such? HA. Well, what do? Look at the one. The degree above and below. What case will that be? Right? What case will that be? Just looking at the degree above and below, what case will this be? Okay?
The second one.
Second one, very good, Eva, right? Case number 2, right? Why case number 2, Eva?
Because the degrees are equal.
They're both 2. You're good, right? They're both equal, right? Degree 1, degree 2, degree 2. Are we good? Right? And again, it says in here, the HA is equal to what? Y is equal to the lead coefficient above and the lead coefficient below, right? What's the lead coefficient above? Logan. 1. There we go. What's the lead coefficient below? 1. There we go. Right? That's it, right? Y is equal to 1. That is your, once again, HA or horizontal asymptote. Are we good? Get it, guys? Okay. Now, what do we do then to get the range, right? So again, the HA corresponds to the range. So what do you think is the range in here? Y, all real numbers except the HA, right? So what's that gonna be? All real numbers, right? -infinity to infinity, except what? 1, right? 1, right? So -infinity to 1, union 1 to infinity. Are we good, guys? Right? Questions? Let's verify it by graphing, right? Where is that, Mr. D, right? Well, let's put it in here. Y equals 1. See that one? That one, guys, right? Okay. That's your, what we call a horizontal asymptote. Get it? Okay. Questions regarding that? Okay, next one. Are there possible removable discontinuity or hole, right? Yeah. Well, we know that the factored form below is x minus 4x plus 2, right? Now, is the one above, x squared plus 4, is it factorable or not? Factorable. X squared plus 4. Actually, not factorable, right? So in short, x squared minus 4 is factorable, right? X plus 2, x minus 2. But x squared plus 4 is not factorable, again, under the real numbers, right? But under imaginary numbers, definitely it can be. We're just talking about the factorable under real numbers. Get it? Right? So in short, is there a hole? None. Right? There's no hole. Right? None. No holes. Okay, guys. Okay, next one. Is there an x-intercept? Right? And what are they? What did it say in there? Where numerator ax is equal to 0, right? What's your numerator? So put in there. What's that again? X squared plus 4 is equal to 0. Just the numerator, right? Okay. What's your answer for x? It's actually what? Plus minus square root of what? -4, right? So again, this is what? Non-real, right? In fact, it's imaginary, right? Which means there's no x-intercept. Get it, right? And again, you can verify it from the graph, right? Did it hit the x-axis? Did not. Right? Did not. Right? And the last one, how do we get the y-intercept, right? How do you get the y-intercept for such? Olivia, let's go ahead. How to consider that? Consider the what? Constant terms, right? Above and below, right? So, what's the constant term above? 4. There we go. What's the constant term below on the denominator? Emma? 8. Negative 8, right? What do you do with those? Just divide them. Get it, right? So in here, it looks like the best option for us is to just look at the constant term, right? And what is that? The y-intercept? Again, this is x-intercept, right? Y-intercept is at what? 4 above, negative 8 below, which is what? Negative 1/2. Is it negative 1/2? Right. Again, can we verify that one in here? Let's check. Are we good, guys? Negative. Right? Now you might be asking, Mr. D, we could have just graphed it all along and actually did the entire thing, right? But again, it says on the instruction a while ago, algebraic, right? So we're just trying to do it as mentioned in there. But again, by just graphing it, you would get the, what already? Key features. Get it? Okay. The last key feature for such will be the what? The behavior or the end behavior, right? Once again, we said a while ago, the left and right end behavior gives you the what? The horizontal asymptote basically gives you the left and right end behavior. So in here, what do we notice for such? What's the right end behavior for this? Right end behavior, look at that. Right end, as x goes to infinity, your y goes to where? Oops. Where's your y going to? What value? What's your horizontal asymptote, guys? 1. Very good. In here is kind of questionable in here because it went down a little bit, alright? So you can verify that one, but basically in here, typically you would say what? As x goes to negative infinity, your y goes to 1 as well, alright? The horizontal asymptote defines, in most cases, the what? The horizontal asymptote defines the left and right end behavior. Are we good? Right. However, the vertical asymptotes gives you the what? The behaviors in here, right? So for example in here, what is this? So in here, we can say in here that what? As x approaches what value? 4, right? As x approaches 4, I would put in here plus, right? If you see that notation, x approaches 4 plus, when you say plus, that means what? From the right. Okay. So from the right, your graph approaches 4, x value, from the right, okay, not 2, from the right, okay? Where is your y going to? Up or down? Up, right? So your y goes to infinity. Got it? Okay. Now, from the left of 4, so in here, see this one in here, right? So as you may notice in here, as x goes to what in here? To 4 as well, but this is minus, right? Okay, the notation minus means what? From left, okay? From the left side, okay? See, from the left, from, okay? Your y goes where? Up or down? Down. Okay. Last two, right? So you do that one for all the vertical asymptotes, right? All vertical asymptotes has the from the right plus and from the left minus. Okay, so in here, from the right, what's this gonna be? In here. So in here, as x approaches what value? Negative 2, right? Okay. Plus means from the right. Okay, so from the right goes there. Where is your y going to? Up or down? Down. That's negative infinity. Okay. And the last one here, right? In here. So as x approaches what? Negative 2 minus in here because it's from left. Again, from, okay? From the left, it's approaching negative 2 for x, right? Where is your y going to in there? Going up. Positive infinity, okay? So verify those on your summary in terms of those notations. You would see that one in here. You see the arrow notation, right? And what it means, okay? And that also explains the plus and the minus on top of those numbers for x. Get it? Again, plus means from the right side, going to that x value. Minus means what? From the left side, going to that x value, not y. Okay? And again, if your y goes up, that's infinity. If your y goes down, negative. Are we good?